Right. Hello. I'm Nikos. I am the lead developer at Robotical. And this talk is about the change we made in MultiBlocks, our Scratch-based programming environment, to support hardware as device targets in the platform we're working. I'm going to cover 5 parts. First, I will introduce Robotical and the coding platform we are working with. Then I will talk a bit about the Scratch idea we're extending, the Scratch target model, and how devices and sprites can coexist within the same system. After that, I will explore a bit the extension approach we initially considered and why extensions alone didn't quite give us the experience we were aiming for. And then I will talk about the architecture we came up with and the reasoning behind it. And to finish, I will show everything working in the demo before wrapping up with a few final thoughts. Right, so Robotical builds educational robots and software for classrooms. One of our robots is Marty, which is a walking, playful robot that learners can use for programming, robotics, and STEM activities. It is packed with LEDs and sensors, and it knows how to dance too. So more recently, we introduced Cog, a newer programmable device with a different set of capabilities. It does have LEDs and sensors, but it really is its own kind of device, so it didn't really make sense to expose the exact same programming interface as Marty. Now, alongside hardware, we also have MultiBlocks, our Scratch-based programming environment, where learners can already build projects there using sprites, blocks, variables, and the rest Scratch entities. Now, the question behind this talk and the problem that we had to solve at Robotical is where do Marty and Cog fit, and how do they fit naturally into that same system? Or more generally, how do we make hardware feel like a first-class part of the experience instead of something bolted on through extensions or like some other programming mode? Right. Before the details on the architecture, I want to pin down the Scratch idea we're extending, the Scratch target model. In Scratch, you first select a thing, and then you write code that belongs to that thing, right? So that thing is a Scratch target. In regular Scratch, we have sprites in the states. When a sprite is selected, you're working with its variables, blocks, custom, sounds. So this becomes the active context. When the state is selected, you're working with the state's behavior instead. Now, that matters because Scratch teaches a local ownership rule, or the object-oriented principle, without making it feel abstract, right? So choose the thing you want to program, reason about that thing, and then write the behavior that belongs to that thing. We wanted the same rule to remain true for Marty and Cog, so the selected device should own its own scripts and variables, also connection status, hardware behavior, while ordinary sprites on the stage should keep behaving the way they used to, the way Scratch users expect. And the design principle for the rest of the talk is extend the Scratch target model instead of hiding device behavior behind some unrelated sprite. Now, why extensions didn't quite cut it? Extensions are useful when you want to add vocabulary, new commands, reporters, variables, and capabilities. The limitation for us was ownership because extension blocks belong to an existing sprite. That might be enough if the hardware commands are simple, but in the case of Marty and Cog, we wanted the device who has its own variables and scripts, connection status, as we said, saved project metadata. If you try forcing all of this through an extension, then the state gets spread across extension internals, GUI state, VM mappings, custom metadata. Now, if none of these ring a bell, don't worry. Just keep from this slide that extensions were not enough for us because of ownership, because extension blocks belong to an existing sprite. And to reiterate the point, the conclusion was not that extensions are wrong, rather the conclusion was that our hardware needed to become a target and not just a set of visible blocks. Right, so device targets were the main architectural change. When a device target is selected, or basically, a device target behaves like a physical target. It has identity, it owns scripts and variables, it can be selected, and it gets a palette scope to do what it can do. SB3 persistence then has to, let me take a step back. SB3 persistence is the Scratch term for the save and load functionality. So SB3 persistence then has to carry the device's metadata, so reopening a project brings back the device program and not just the blocks. Now the implementation separates two questions. The target type answers the broad programming model question, is this a sprite, the stage, or a device? And that lets the editor treat hardware as another target without confusing it with sprites. The device type answers the hardware-specific question, what kind of device it is. Mart and Cog are both devices, but each has its own variables and behavior. Now we saw that classic Scratch gives us sprites and the stage. Device targets add another branch. When the selected target is a sprite or at the stage, regular Scratch behavior remains intact. When the selected target is a device, the toolbox can now show blocks that belong to that device or that make sense to that, for that device. That keeps the environment from becoming, one large mixed hardware palette. The selected target sort of drives tools visibility. So the editing experience can maintain the same rule we said before. Select the thing you want to program and then write or see the variables and the context that belong to that thing. Right now, so the same concept needs to be understood by several layers. The GUI is responsible for displaying and selecting the target. The toolbox is responsible for filtering the blocks based on the selected target. The VM is responsible for creating, managing, and serializing the target. And the hardware layer is responsible for binding the physical target to the logical device, basically, to a physical device when one is connected. That's why the change could not live in only one place, because if only the extension knows about the device, then the UI and saved program do not have a stable owner for the scripts. Right, so another split is that between the saved project identity and the live hardware connection. The target ID is the saved project identity. It says, or it can say, this project has a Marty or this project has a Cog. It needs to remain stable across save and load, and it needs to remain meaningful even when no hardware is connected. Now, on the other hand, the device ID is the live hardware connection identity. It can change. For example, a Bluetooth connection can drop, a robot can be switched off, or a different device might reconnect later. Now, keeping the target ID and the device ID separate makes classroom cases easier, because now the project can be shared, can be opened without hardware, reopened later with a different hardware device, or run against the simulator first. So the saved program and the physical connections are related but are not the same thing, and that separation makes the reconnect and save and load functionalities less brittle. And now I'm going to do the live demo. Let me switch on Marty over here and Cog. Right, so this should already be familiar. It's just the Scratch platform, the Robotical's adaptation of the Scratch platform. I want to draw your attention on this place, where the stage is, sprites, and the devices panel, which is where the user can manage their devices. So I will start by adding a sprite. I'm going to add an Apple sprite, and then a device for Marty, and one for Cog. Right, so one thing that you might already notice is that when I'm clicking through the different targets, the toolbox shows blocks that make sense for that device. This is a Scratch-like behavior, but this is what this demo is about. That how we fit like Mart and Cog naturally So by maintaining like the same Scratch approach, if that makes sense. Oh, let me just connect to Marty, and then I'll connect to Cog as well. And I'm going to create a very simple program just to demonstrate, just to have the different targets communicate with each other, to show how this is possible by upholding the same Scratch rule, the object-oriented principle we talked about. So I will start from Cog, and I'm going to add a new block. On button press. So Cog has a button on the top, and when that button is pressed, this event block is going to be triggered. And when that happens, I'm going to broadcast a message called message1. Now, from the Apple side, I'm going to be listening for that message. And when I receive that message, I'm going to have the Apple say hello. And then from the Marta side, I am going to, again, be listening for that event. And then when I do get that event, I'm going to have Marty wave the arm. And yeah, that's it. Again, just very simple program with a couple of blocks for its target. And now I'm going to press Cog's button, and you see Marty's waving, and the Apple up there says hello. Again, nothing fancy, nothing extreme, just a simple demo to show you, how the whole thing like fits together. And I'm going to get back to the presentation and wrap it up with that final slide. So what should someone else take from this? First of all, not every hardware device needs to become a target. If the hardware only requires a few commands or reporters, then I guess the extensions approach or some other programming mode might still be the right fit. This model starts to make sense when the hardware needs to be selected, needs to own its own scripts and variables, needs to be able to be saved in a program, and then reopen the same project with the same hardware device or some other device. And basically something that I forgot to mention before is now with that model, the user can add multiple devices of the same type or of a different type. So I could have like a bunch of Martys connected to Marty blocks and have them interact with one another, play football or whatever. The adoption path really begins by deciding if your hardware needs to become a target, and if that is settled, then the rest layers, GUI, VM, persistence layer, toolbox, hardware layer, all these needs to line up based on the architecture we discussed above. And thank you. That was me.